Hello everyone. I would like to discuss some of the properties of trapezoids, including the definition. And then after that, I want to do an example of just verifying that something is a trapezoid in the coordinate plane. So first thing, let's start with the definition of a trapezoid. The definition is this is a quadrilateral that has exactly one pair of parallel sides. So quadrilateral with exactly one pair of parallel sides. So we talked about parallelograms a lot, and they have two pairs of parallel sides. Now this is a little bit different. This has exactly one pair. So now we're looking at something. We just draw a little diagram to go with this. So maybe the top and the bottom of this trapezoid are parallel to each other, and then our other pair of sides are strictly not parallel. So something like this. So then we have one pair of parallel sides. Okay. Now, just a couple of the parts, a couple of the pieces of trapezoids. These two sides that are parallel, we call these the bases. So this is a base, and that side's a base. The other two sides we call the legs of a trapezoid. And then the angles, two consecutive angles that are along one of the parallel sides. So these two angles, I would say this is a pair of base angles. And then along the top, these two angles together, that pair, that is a pair of base angles as well. Okay? Now, besides the pair of parallel sides, a regular trapezoid, there's not too many other properties going on. With the parallel sides, we do have supplementary angles. These are consecutive interior angles, so these are supplements. But more interesting is isosceles trapezoids. So an isosceles trapezoid is when the legs are also congruent, kind of like an isosceles triangle. So let me do my best to make this isosceles. Okay, so we have the one pair parallel sides, and then the two legs of this trapezoid. So these are parallel, and then the legs are congruent. So the definition here, this is a trapezoid with congruent legs. Okay. Now, when we have an isosceles trapezoid, this is where we get some interesting properties. So we have some theorems that will give us some properties. So the first theorem is the isosceles trapezoid base angles theorem. And this says that the base angles are congruent. So I'm actually going to label this trapezoid so I can refer to its parts here. So in an isosceles trapezoid, the pairs of base angles are congruent. So that means angle A and angle D are congruent to each other, and then angle B and angle C are congruent. And the converse to this is actually true. So if we know that we have an isosceles trapezoid, that means that these base angles are congruent, but it also works backwards. So if I have a trapezoid, forgot I should put angles in here. If I know that the base angles are congruent to each other, that means that it has to be isosceles trapezoid. So if base angles are congruent, this leads to it has to be an isosceles trapezoid. So those kind of go hand in hand together. The third and final theorem, the other special property of isosceles trapezoids, deals with the diagonals. So in an isosceles trapezoid, the diagonals are congruent. So that means in my trapezoid here, the diagonal from B to D, that length is exactly the same as the diagonal from A to C. So that means AC is congruent to BD. And this one also works the other way. So this is an if and only if statement as well. So if I have an isosceles trapezoid, then the diagonals are congruent, or vice versa. If the diagonals are congruent, it has to be isosceles. All right, so now that we know a little bit about trapezoids, you know some of their properties, let's take a look at an example in the coordinate plane. Okay, so this says show that ABCD is a trapezoid, and then we want to decide whether or not it is isosceles. So I was given these coordinates, and then I went ahead and I graphed that trapezoid already. Now, to verify that it is a trapezoid, the easiest way to do that is by using the definition. And the definition is we have one pair of parallel sides. So we just want to show that for all four sides here, there's only one pair that is parallel. And in the coordinate plane, the easiest way to do that is by using the slope. So as a reminder, your slope formula subtract the y's on top, subtract the x's on bottom. Or if you have it graphed nicely, you can just count the slopes as well. But I'm just going to go through, and for all four sides, let's figure out the slopes. So AB, so our first two here, let's see, we'll just subtract the y values, 9 minus 6, and then the two x values, 4 minus a negative 5, so that turns into plus 5. So we get 3 over 9, which is 1/3. And then I was going to make my way around the trapezoid, or hopefully trapezoid. And let's see, so our second segment, BC, so we have 4 minus 9 for the y values, and then 4 minus 4. So that gives us negative 5 over 0, which is undefined. Okay, so this is actually a vertical segment here. All right, and then let's take a look at CD. Now, just kind of looking at the picture, I'm hoping that CD has the same slope as AB, because those two sides do look parallel to me. So 2 minus 4, and then our x value is negative 2 minus 4. So let's see, that's negative 2 over negative 6, and that does work out to 1/3. And then our last one, AD, our slope here, so we got 2 minus 6, and then negative 2 minus a negative 5. So 2 minus 6, we get negative 4 over 3. Okay, so taking a look at all of our slopes, there's only 2 that match. So that means we only have one pair of parallel sides. So let's just summarize that a little bit here. So let's say using the slopes, there is only one pair of parallel sides. Only one pair of parallel sides. And that is that AB is parallel to CD. So that means that ABCD is a trapezoid by the definition. Great. Now for the second part of the question, we want to show that this is isosceles. The definition then would be that these two segments, the two legs of the trapezoid, have to be congruent to each other. So I could use the distance formula for those two sides to figure it out. Or, we do have options here. One of the properties you talked about is that the diagonals have to have the same length. So we could test these lengths out as well. So why don't we do that? So let's figure out the length of AC. We can use the distance formula. So let's see, we subtract our x values. We got 4 minus a negative 5. And then our two y values, 4 minus 6. So we get, that's 9 squared, and then plus a negative 2 squared. So 81 plus 4, so AC is the square root of 85. And then let's do the same thing for the other diagonal. So for BD. So let's see our two x values. Let's see, so we got negative 2 minus 4. And then our two y values, we got 2 minus 9. So let's see, that's going to be a negative 6 squared plus a negative 7 squared. So that is 36 plus 49. And that is also 85. Okay, so the diagonals end up having the same length. So the diagonals are equal. So AC is equal to BD. That means that ABCD is isosceles. So using our theorem, using the property of isosceles trapezoids, we can verify that yes, this is isosceles.